Okay, thank you very much for coming. Let me make a short introduction, or not so short introduction, and then we will start. So, dear colleagues, students and friends, it is a pleasure to have here again my friend Professor Bjarne Stroustrup. As many of you know, Professor Stroustrup is the creator of the C++ programming language and one of the most prominent figures in history of computer science. Let me briefly give you some details about the impressive trajectory of Professor Stroustrup. Some of you probably know what I am about to say, but I may give some new information, especially to the younger audience. Professor Stroustrup holds a bachelor in mathematics. Well, he will correct me and tell that is a candidate something, the Danish word.
It's more like a master's.
Yeah. In computer science, in mathematics with computer science from University of Aarhus, his hometown in Denmark. During this period, he learned the fundamentals of object-oriented programming from Christian Nygaard, the co-inventor of Simula and the co-inventor of object-oriented programming itself. In 1975, he moved to Cambridge, where he started his PhD under the supervision of David A. Wheeler. The name of David Wheeler may be familiar to you, as he was acknowledged to be the inventor of the subroutine. Now, somebody had to invent the subroutine. Or perhaps because he is the original author of what many refer as the fundamental theorem of software engineering, probably a bit grandiloquently. All problems in computer science can be solved by another level of indirection. As Bjarne has always reminded me, the quote as it is incomplete, as you need to add except the problem of too many layers of indirection. In 1979, he moved to the US and joined Bell Labs at AT&T, where later he would become the head of the large-scale programming research department. In 1979, at that time, he was able to interact with Brian Kernighan and Dennis Ritchie, the inventors of the C language, as well as many other legends in history of computing. I have more. Between 1979 and 1980, he started developing what would be C with classes. By 1983, this led to the first version of the C++ programming language. The first translator of C++, C-front, was just a preprocessor generating C code that would be then compiled by a C compiler. From then, things moved quickly. In 1986, C++ had around 2,000 users around the world. In 1989, C-front 2.0 was released. Then other implementations came. A few months later, in 1990, the annotated reference manual was published. It would be used as the basis for the standardization process initially started in 1989 as an ANSI, an American standard, with the participation initially from HP, AT&T, DEC, and IBM. In 1991, international standardization was started under the umbrella of ISO. By that year, the number of shipped compilers by a single company, Borland, was reported to be around 500,000. Estimating the number of users today is difficult, but most estimations are above 6 or 7 million programmers in the world. Personally, I consider those figures quite conservative. If you want to know more details about the early history of C++, I would strongly recommend that you read the book The Design and Evolution of C++ from year 1994. that is wonderfully written with a very nice combination of history, explanations, and source code. There is a conference organized by ACM under the name HOPL, H-O-P-L, which stands for History of Programming Languages. This is a very special conference. It only happens roughly once every 15 years. So there have been 4 editions in 1978, 1993, 2007, and 2021. And papers are submitted there only by invitation. To the best of my knowledge, Bjarne Stroustrup is the only language author that has been invited in 3 consecutive editions. Well, he could not be in 1978 because he started the thing in 1979. And in 2002, Professor Stroustrup left AT&T and joined University of Texas A&M, where he stayed until 2014. And he continued working in research and making contributions to the C++ programming language. He also made major improvements in the way programming can be taught, training generations of engineers. He wrote the book Programming Principles and Practice Using C++, which is a fantastic book that I recommend for learning how to program in general. It just has a little detail that all the examples are written in C++. The 3rd edition of this book has been published last year in 2024 and is quite up to date. In 2014, he joined Morgan Stanley as a managing director. Morgan Stanley is a major player, as you may know, in financial industry, and he joined at the office in New York City. At the same time, he was a visiting professor at Columbia University. That led him to new opportunities to interact with real, large-scale industrial projects. In 2022, he retired from Morgan Stanley. He is currently a full professor at University of Columbia. Professor Stroustrup holds a honorary doctorate by University Carlos III de Madrid. He holds many awards and honors. Let me enumerate only some of them. In 1993, he got the ACM Gates Murray Hopper Award for his early contributions to the C++ programming language. In 2017, the Faraday Medal from the IET for his significant contributions to the history of computing. In 2018, the IEEE Computing Engineering Award for bringing object-oriented programming and generic programming to the mainstream. And that year, he also received the Charles Stark Draper Prize from the US National Academy of Engineering for conceptualizing and developing the C++ programming language. After all this impressive trajectory, you might think that he is done. Let me tell you that he is a hard worker. Currently, he is really very involved in improving the safety of the C++ programming language. He participates in every meeting of the C++ Standards Committee. We meet 3 times every year, and each meeting is 6 full days. When I say full days, I mean that some days we even have evening sessions after dinner. If that was not enough, he travels all around the world to give talks and participates in conferences about C++ programming language. Please let me thank Bjarne Stroustrup for giving us the C++ programming language and for all the contributions to computer science. The other day I said, and I strongly believe it, that our civilization, as we know today, is heavily based on the C++ programming language. I usually would say that all of you have used C++ today. When you use your maps application to get here, when you use your phone for whatever. But those are typical cases. it is much more than that. Last week, I learned that without C++, you would probably not have been able to get a glass of milk this morning. So, Bjarne, thank you for everything, including my daily glass of milk. Let's give a warm welcome to Professor Bjarne Stroustrup.
Thank you very much. It's a little bit hard to say anything after such an introduction, but the purpose of my talk is to try and explain to you how C++ today can be used to build interesting, good, reliable systems. So I tried to make C++ so that it could be used to do things that I couldn't imagine. That is, it was supposed to be a system that could express useful things beyond the imagination of any one person. Which means you can do just about anything. But think about Goto. A Goto can do anything. This is why we don't use it. We have to use some framework for what is good and how you use it. And so I'm going to try and look at C++ to see which parts have proven useful and guide people to use it right. And the point here being that C++ was designed to evolve, was designed to be improved. I knew I couldn't write the perfect language back in 79. As a matter of fact, I don't believe that a perfect programming language can exist, because perfect relative to what? The world changes, we change, our understanding of things changes. However, I know that modern C++, contemporary C++, can express just about any problem clearer, simpler than could be done earlier, and usually running faster. And of course, usually running faster than anything else. So I'm trying to encourage you not to confuse what is familiar with what is simple. Quite often people look at things that are new, radically new, fundamentally new, and think it's very complicated because they translate it internally into the old stuff that it was meant to replace. I just saw something on LinkedIn yesterday where people were discussing a radically new system for building web applications that build systems that are easier to build by 2 orders of magnitude, served 2 orders of magnitude more users in the same, on a small computer. And people just didn't believe it, or they believed it did something completely different, or that there was some hype going on there. No, somebody's had some brilliant new ideas, and people couldn't quite understand it. It wasn't familiar. So sometimes you have to learn something new. You have to think in new ways to make radical improvement and important new improvements. I mean, when I started with C++, there was languages like C and COBOL and Pascal around. We don't build systems like that anymore. We can do much better, but it means that we have to learn new things along the way. So let me show you some new code. And those of you who have been writing C++ for ages might think this is sort of strange, but this is what we can do. Here is a program. Alejo, my friend who did a lot of fundamental stuff in compilers, got a Turing Award a couple of years ago, sent this program to me. Let's see. That program there in org, which simply writes out every unique line in a program. And so, can I do that? Yeah, I can do that. First, I import std. We don't have to use includes anymore. We have modules. I'll get to that later. And I'm using namespace std because I'm a bad typist and don't like to write std : all the time. And then there's main, of course. So I take an unordered map of strings and integers. So basically, I'm going to read things in. I'm going to see if I've seen it before, in which case we've got it, and the count is 1. So basically, read lines in, see if the count is 0, so we haven't seen it before, and write it back out again. And it is something that people do sometimes for log files and such, so it's not a totally unrealistic program. But notice what's not there. This is important. No allocations, deallocations, no sizes, no error handling, no type conversions, no pointers, no preprocessor. I like that. And it's quite efficient. It's as efficient as you would expect in a high-level scripting language. And you know, importantly, if you want it to run faster, you can tune it. One of the themes of this talk is that you can write things at a high level and then tune it if you need to, if you've designed your interfaces right. So let's try and make it a little bit more general. Let's have a function that stores the unique lines for further use. So I have to have a collect line file. It takes an input stream, creates a vector of strings. Vectors are the most useful general way of storing things. So we'll have a vector of strings. We'd make an unordered set of strings. We don't need to count anymore because when we put something into a set, it doesn't have copies. So read them into read the lines into the line, and then put the line into the set, and then we copy the vector out of the set. The vector's element type is deduced because the compiler already knows that. One of the things in modern C++ is that we don't like you to repeat things that you have already said. The compiler remembers what you said and uses it. None of this repetitive stuff. So I say collect the lines, and then I use a range for loop to output the lines if that was what I wanted to do. There's many other things we can do. So apparently a lot of copying going on. I mean, we copy the lines into the set. We copy the lines from the set to the vector, but we'll optimize that if we need to. This is as good or better than what you can do in most languages. Okay, so let's see, what are we trying to do? Or what am I trying to do? I want to have the most direct expression of ideas that I can get. I really like to be able to say what I want done. I don't want to be the compiler and break the things down into pointers and bits and bytes and characters and things like that. I want to be able to say things like, I want to collect the lines and have the details done and then do that recursively down. I want static type safety. C++ was built out of C for low-level efficiency and Simula for being able to express ideas. Simula is statically type safe, and that is the ideal. It always was the idea. But when you have to deal with hardware, you really have to deal with bits and bytes and interfaces and such. So somewhere there has to be an escape from the type system. I want resource safety. I came from operating systems, machine architecture. I have friends who build spaceships. You really don't want a resource leak. You cannot send a repairman to Mars. And if you could, it would be too expensive. So you really don't want to leak things. People talk about memory leaks and such. But you know, I can crash a machine much faster than leaking memory. My favorite is to leak file handles. That'll get the operating system in a few microseconds. So I don't want resource leaks. I want direct access to hardware because there's a lot of interesting stuff going on if you can play with the hardware. And a lot of the gadgets we have, well, there's hardware, there's phones, there's cars, there's airplanes, there's coffee machines, and there's lots of things like that. I want performance. If you are slow, if you have a lot of indirections, if you do a lot of spurious work, you need a bigger computer, you need a bigger battery, you need another server farm or something like that. We need performance, aka efficiency, to get things done. And then I have the principle that I sort of named, what you don't use, you don't pay for. There's a lot of languages that has a lot of stuff there just in case you need it, and it's there even if you don't need it and you end up paying for it in runtime or memory size, things like that. And affordable extensibility. I want to be able to get away from the hardware. Once you use the hardware, yes, that's essential, it's important, but it's also an unpleasant level to write code at. Dealing with bytes and pointers and memory addresses and stuff, this is where you make mistakes and you have to fix them, and then it's midnight and you've missed the party or whatever it is. You really don't want to be there as longer than you can. You want to increase the level of abstraction. When you get to the next level, you want to increase the level of abstraction again. So affordable extensibility. It's not enough to be able to extend what you say. You have to be able to afford to do it. We need concurrency support because this concurrency at so many levels in the world. I mean, that thing has 18 cores, and that's a small little computer that fits in an economy-sized seat in a plane. There are so many levels. I can't talk about that today. I have one slide apologizing for not talking more about it, but really we need a whole talk for that, or a whole day, or a whole course for that, because concurrency in many forms is very important. I want maintainability. A lot of people build stuff that lasts for decades, and you have to have stability for that. You have to have facilities that can be used for that, can be used for tuning, can be used for porting. Hardware change needs change. And that's sort of it. And basically contemporary C++ can deliver this much better than the early C++. There's a picture from the ages where I had a little bit more hair. So contemporary C++ is not just novel features. If you go to, say, YouTube, you find a lot of talks that is about how this new feature is going to be great and it's going to help everybody and you're going to use it all the time. And so you get people who get this idea that if a feature was in C++ 14, it must be old and can't be used anymore. And I think this is fundamentally wrong. The language has evolved with improvements in certain areas, but there's fundamental things that solves fundamental problems that actually hasn't changed. So there's some key features that are really old. Classes with constructors, destructors is the basis of C++, and it still is. It's absolutely essential in most modern C++ programs. Exceptions, templates, standard vector, It's all quite old, and it is, well, it came in because it was necessary, and it still is. And there's lots of more modern things. I'm going to talk about modules. I'm going to talk about concepts for specifying requirements for template arguments, lambdas for defining functions, exactly where they are used, ranges and such. Lots of modern stuff also. But the point is that C++ is not basically a layer cake where you use the latest layer. You are using the features that integrates over time and over your code. And I'm going to focus, of course, on the later features because some of you don't know them and some of you don't know where they fit. So it's a little bit more emphasis on that, but still, that's it. If you write code, don't use every new feature. Don't use only new features. So back to what I want. I want applications. I want good use of the language. The value of a programming language is the range and quality of its applications. And there really are a lot. I see here there's some pictures of it. If you like, if you like Hollywood movies, they'll be using that software. If you like, say, server farms like Facebook or Google, something like that. If your car needs to help find the way, there's something there. Oh yeah, the car is built. That's a distributed computing system with about 250 processors. If you like AI, there's a couple of things here. There's TensorFlow, and there's DeepSeek. There's C++ programs. So I'm not an AI expert, but made a contribution somehow. And I'm not going to go into language wars. There's some very interesting languages that have been built using C++. Most languages use C++ somewhere, either in their implementation techniques or in their libraries and things like that. Did I see Python somewhere? Anyway, so here I'm going to focus on resource management, on modules, and generic programming, and then I'm going to talk about the important thing about how do you actually stay into the sane part of C++? How do you actually use the appropriate features for a problem? And that's where I'm going to get to. I have a book for experts that focuses on that kind of stuff, so you can read it. Oh dear, I forgot to put the Spanish version on the slides. Sorry about that. Just proves that I'm not actually trying to suck up to you. There is a Spanish version. So let's look at resource management. A resource is anything that you must acquire to use, and then you have to give back again when you're finished. And we know that people are not very good at giving back things they borrowed. I mean, ask any librarian, right? So we would like for giving back, for releasing things to be implicit. You ask for something, and then at the end of the scope or whatever, at the end of the time where you use it, it automatically goes back where it came from. And that's what we do. We want to avoid resource leak. This is important. And the way we tend to do that is we represent a resource by a handle that points to whatever it really is. I mean, this could be memory, this could be a file, this could be a lock, it could be a shader in a graphics system, something like that. And every resource handle we root in a scope so that when we are out of the scope, it gets cleaned up. So here's the simplest example I know of. It's a vector. A vector of elements of type T and we can create a vector, and here's the implementation of the vector. So basically we start out at the low level with pointers and sizes. We're down at the hardware. We use the hardware basically optimally, and then we raise it to a level where it's easier to manipulate. The constructor builds up a vector, and the destructor destroys it. And so we can use this by saying I want a vector of doubles of some well-known concepts, a vector of strings of some well-known designers, I hope well-known designers. There's Dennis from C. Let's see, vector of pair of strings and threads. I'm making a pipeline here, and the point is that this actually goes rather deep because pair has a constructor, destructor pair like that, string has it, JThread has it, and it'll all be constructed from here, and right there everything gets cleaned up in the proper order at the proper time. Somebody had a competition about what their favorite C++ feature was, and the winner, I think, was Roger Orr, who submitted just that character. That's where all the magic happens. This is where C++ differs from essentially all other languages. It cleans up its messes when you come to the end of the scope. Okay, so what we're doing here is we're controlling the lifetime of objects. We can construct, we can destruct, we can copy things, and we can move things. The difference between copy and move is quite simple. If you are into sort of computer science and you make a copy, you always make a copy, and at the end of the scope you'll have to, or something, you have to destroy the original. Now, only a computer scientist would do that. Babies age 6 months knows that if here's an object, now it's over there. I didn't make a copy, I didn't destroy anything, I just moved it. And so C++ reflects this. If you want a copy, you get a copy. If you move it, you move it. Fine. And oh yeah, the pictures I have here illustrate some use of C++, sometimes interesting ones, sometimes fairly traditional ones. Anyway, I visited CERN at some point, and it's a lot of fun C++ there in high energy physics, and in the very impressive engineering that goes on in that kind of physics. So let's go back and I'm worried about copying that early example. And so I'm collecting the lines into a vector of strings, and I would like to do less copying. So I make a line, read it, insert in a string, and copy the vector out. And the worst case here now is that we build res here, and then we steal the representation, the elements of the res, and put it into lines, and then we make sure that the destructor of res doesn't destroy anything. So basically, if I'm now returning, say, 1 million lines, the maximum cost of that copy there is 6 word instructions. 3 to make the copy of the representation, the pointer, and 3 to make sure that the destructor doesn't do any harm. However, we can do even better. Our next slide will show that. So here I'm making the simplifying this. There's a way of dealing with ranges that optimize manipulation of ranges, including infinite ranges. So here I'm saying make the unordered set from the lines you read from input. I mean, I like simplifying code. That's actually fairly complicated code when you think of it. Here I'm saying just get the lines from the input and don't copy them twice. and then we return the vector that you get from the set. Fine, and we do this. Now, we can actually do better than a move here. Back in 1983, I noticed a problem with a slight overhead relative to C, and I removed it. And the trick here is to notice that when I'm returning this one, I'm going to place it in lines. Why have something local? We just build it in lines. The compiler knows enough about that. So basically, we construct the vector in the location of lines, and we're done. So those 6 instructions, that was the worst case example of how you deliver 1 million lines of lines, goes away. 0. I like that. 0 overhead abstraction. We've got it. This really means 0. Okay, so that's fine. The only problem is, oops, let me just show you line. There's no line in the standard library. There's strings, but there's no sort of line. So I needed one because I'm thinking about lines. I'm talking about lines like log entries and such. They're lines. So we build a line. Here, a line is a kind of string, and it's a kind of string that you read with getLine instead of other ways of doing it. This is classical object-oriented programming, thanks to Christian Nygaard and Simula and such. And so this is conventional. Some people forget about these things, but one thing that's important here, you don't just use libraries. You can write your own extensions to just about anything, and you can use the techniques that has proven useful over the decades to do so. And this is building an abstraction. That's 2 lines. This is not bad for a fast implementation. Okay, so now there's only one thing left here with the optimization. We actually copied the strings from the set into the vector. And that's expensive. Copying strings is expensive. If there was 1 million lines, you'd be able to feel it. And you can get rid of that. There's a notion of moves. I mentioned moves before. String has a move constructor. Now we just have to tell the system to use it. And here, this is an explicit optimization. I just say, instead of copy, move. The compiler will not know that. It could in theory, but in practice they don't. Last time I checked the compilers, they weren't smart enough to do that themselves. And now I can do this with essentially 0 copying. We have now optimized the simple example of collecting strings from the sort of the level of scripting languages to something that will outperform C. Okay, so anyway, don't optimize unless you know it's important. That is, for just about any use I have of this, I don't need all of these optimizations. This is something I do if I discover that I use this program a lot and it matters how fast it runs. How do I know? I don't try to be clever. I don't try and guess what it is. Measure. When people talk about efficiency, ask them, what did you measure? What were the results? Why does it matter? So it's very important to measure things before you optimize. Keep the code clean, keep the code high level, keep the code so that you can tune if you need to run faster, and then measure. Okay, now this is my version of the old do not optimize prematurely. I like prematurely. That is, you start designing nice things and then you tune if you know that you can do it. And basically, this is a way of managing complexity. It gives layers of abstraction. You saw it with the collecting lines, but it's something that works fairly general. You have a really nice interface. It has all the information needed to do tuning. If you need to tune, you peel off a layer and you work there. If that's not good enough, you peel off another layer and it runs faster if you do it right. And you keep going on. You can go on all the way down to building FPGAs or something to get things running. Your user interface, what your user sees, is still the same. I call this the onion principle because each time you peel off a layer, you have to write more code and you have more optimization, more opportunities for making mistakes. In other words, you cry more. Okay, so resources and errors. Now, a lot of code, a lot of systems are sort of 50 or 90% error handling. So we can't just talk about how the code looks when everything's fine. We have to deal with errors of all sorts, and we have to have a strategy for that. And I distinguish between what you do, when you discover an error and how you percolate that error up if you can't handle it locally. So when an error happened, before exiting the function where you discovered it, put every object accessed into a valid state so that you know your system is in a state where you can actually do things with it later. If you leave messes around, you can't recover anyway. And release every object that function owns. We don't want to leak anything. Okay, so here's an example. I have a gadget type. And for now, I'm not going to tell you what the gadget type is. As a matter of fact, I don't know, because this is just an example here. But you know, that gadget here may take locks, it may have file handles, it may have a variety of data structures. Okay, and here I'm doing the traditional way of doing this in languages starting from Simula. A lot of languages like to use a new operator to say this is something for a user-defined type. It has to live on the heap, on the free store, on the dynamic memory. And so they write code like that. And for years I saw more and more of it as people learned Java and C# and thought it was cool to write new. The problem is here, that's not an owner, it's just a pointer. Anyway, so we come here, and if we throw, we are leaking that gadget. If we throw here, we are leaking, if we return, we are leaking that gadget. And unless there's a delete PG here, we're actually leaking it down there also. So people say, give me a garbage collector. Well, there's two things wrong with a garbage collector here. First, it doesn't know anything about the locks and the file handles. So it's an incomplete solution. Secondly, with a garbage collector, you are not cleaning up the mess there. You're waiting for an indeterminate time to figure out when you need to clean up. And maybe it doesn't get called, and then the locks and the file handles are not dealt with. So anyway, local objects also tend to be faster than objects on the free store. There's an allocation and deallocation that's not done. So it's fine. So basically, don't use explicit new. News belong inside resource managers. They belong inside in the implementation of a vector, implementation of a list, and implementation of a gadget, whatever a gadget is. Okay, so that's fine. And so when you're dealing with errors, you have to have an articulated error handling policy. Error codes you use for for things that can be handled locally. If I ask to open a file, I really should. I suspect that file doesn't want to get open or doesn't exist or something like that. If you write code that opens files or acquires things that you know might not be there, you should do a local handling. So you have a function, it has to return an error code and whatever else it's going to do, and so you do that. However, lots of errors you can't predict. They are not common. They happen once in a billion times or something like that. And if you start checking every time, you are doing a lot of extra work. And you also tend to forget to test for unusual, unreasonable errors. For those of you who write old-fashioned C++ or C, when did you last check the return value of printf? That's the one that is supposed to tell you, that's the one that tells you whether the print actually succeeded. Now, in the old days, prints always succeeded. But with networks in the place and your output going elsewhere, once in a blue moon, the output didn't happen. And is your system resilient to output that just doesn't happen? Files that doesn't contain information you were supposed to contain because the writes didn't happen. So for those kinds of things, I think we need exceptions that percolate up to a point where reasonable error handling can be handled, can be done, and also doesn't force you to test things all the time. I think the error code hell is where you really have to test every function you did for whether it succeeded or not. And by and large, you do not know which functions can succeed or cannot succeed. One of my favorite examples has been a system that was built on a single system, single machine, and then it got to use a network file system. And now suddenly errors from machines that you'd never heard of and kinds of errors that you've never heard of start percolating through the system. I don't want to test that every time. Okay, so for some important applications, unconditional immediate determination is not an option. I mention this because there's people that says, well, if you can't handle things locally, just crash. I know two kinds of systems where this is an unacceptable solution. One that I know personally, you have a file transaction. It's trying to put some money into your bank account, and the system finds an error and it crashes. If that's all that happens, you're going to be very unhappy. The money just evaporated. There's actually laws against that. But the point is that you need to at least go and record that a certain transaction didn't complete, things like that. So there's a fair number of such programs out there. A friend of mine has a more graphical example. He says, I was dealing with air controllers for scuba divers. There's only one processor. Don't crash it. That would be a fatal mistake. Anyway, so there are things like that. So you have local handling of errors, you have exception-based non-local error handling, and then you have cases where you can simply crash and have multiprocessor systems where another processor picks up the problem and such. If you are into, say, fighter planes, you have to have systems that are resilient to bullet holes. And that's where you have to think about termination, but you can't have the whole system top. So error handling. If you use error handling based on the resource management that we saw, it's usually called RAII, resource acquisition is initialization, you can use that. It's can be far cheaper and faster than using error codes because you have to keep testing the error codes. And if you don't, your code looks simpler, but you don't handle the errors. There's a very nice paper recently that shows it can actually, exception handling can be faster. Even in firmware, this was an example done in very small systems. It has been proven for a long time in larger systems, but this one is interesting. So here's an example. Here's a piece of code that follows the rules I said. I open a file here, and of course I test this immediately. But in all the other cases, I'm not doing any testing because, well, I don't need to, and I can't really do it in a file like this. There's no place to have a return code. There's a plus there. I'm adding Dennis's first name to his second. How do I actually test whether that succeeded or not? If I had to do this with return values coming back and testing the return values, it would be a filthy mess and it wouldn't fit on this slide. So let's go to something more modern, modules. One thing that I and many others have disliked for decades is the include files, the header files. So I'm including A, I'm including B, and I can, if somebody else includes B and includes A, you might get a different meaning. Because A can affect B and B can affect A. You get bugs that way. Not very many bugs, not very frequent bugs, but because they're infrequent, people don't suspect them, people don't notice them in time, you get bugs. The other thing is include is transitive. You simply grab the text and put it in there, and each time you do that, you get a bigger and bigger thing for the compiler to deal with. Compilers are good, but they do a lot of works. Today we can do better. We make a module A and a module B, and it has the same meaning for B and A. You can't get the subtle dependency bugs, and import is not transitive, which means that if I import something and then export to you, you are not dependent on what I imported. Whereas if you do it with include files, you certainly have access to all kinds of interesting and uninteresting things. That's the bug source. So much compilation can be done once only, and you have a proper interface that doesn't leak information. So let's see an example here. I want to make a map printer. I import I/O streams, I import containers. You've never heard of those, and you're not supposed to, but you aren't going to hear them either. I'm using namespace std. Putting that in a header file is a major mistake, but you know, this doesn't leak, so it's fine. I am leaking, or I'm exporting only the function I want to export. The print map, I take anything that has a sequence. We'll get to concepts later and how that's specified. And then I go through, for all M sequences have key value pairs, so I write them out. That's done. And all that is seen is this implementation here. So that's fine. Let's see. It's not. There's some effects here. It's not just for the standard library. I used my own library previous to thing before, but some people think that modules is just the standard libraries kind of stuff. It isn't. Here's an example. I borrowed it from Daniel Eckert, Contemporary C++ in Action. She was actually here on Friday giving a talk. So for the first time I showed this slide to her, so it's fine. Anyway, she's working on some embedded systems in Germany. They have a library there. It's a bit hard to read, but anyway, they are using a device, and that library is a big library. It's about 500,000 lines of code, a lot of blank lines, and the compiler can do that 500,000 lines in a second and a half. Compilers are actually pretty fast these days. Second and a half is not bad, but you may include that library in 100 files, and there may be 100 libraries you include. You can feel it. And there's chances of bugs. When you go to modules, you just import it, and then you use it. 5 lines of code, 1 blank line, and it takes 62 milliseconds. In other words, it compiles 25 times faster. This is good. This is what we expected. Don't expect all of your code to speed up by a factor of 25. I have seen from zero improvement to 100 times improvement. It varies in between. I usually think about 7 as a default. We are compiling 7 times faster or 25 times faster than we used to. This is the kind of stuff that people running compiler farms really like, and I guess I drink less coffee now because I don't have to wait for this. So I wanted to do a little bit of experiment, and I wanted to get into the standard, so I proposed a namespace STD that you saw earlier, and I did some measurement. I wanted hello world, which I can implement with IOString, or I can implement with import. And including it, compiling hello world on an old laptop of mine, took almost a second, whereas it took about a 1/10 of a second with the import. So I am importing at least 10 times as much information, making available at least 10 times as much information, and I'm doing it in 100ths of the time. When I do little experiments with code and such, I always use this because it's much, much faster. I did the other experiment where I included and imported a lot of things there. It was only a factor of 5, but still, this is significant. Okay, so we have resource management, we have error handling, we have faster compilations with fewer bugs. So let's look at improving generic programming. Generic programming in C++ started a long, long time ago. I did something back in the early days using macros. Didn't work very well. Alex Stefanov is the father of modern generic programming in C++. Basically gives shorter, more readable code. It's more direct expression of ideas. I can say I want a vector of t, where t is a parameter, as opposed to having specific vectors of this, that, and other. Less code, more directly expressed. Zero overhead abstraction. We can optimize this stuff away. It's type safe. It's pervasive in the standard library. We have containers, algorithms. All the concurrency stuff is parameterized. I/O, strings, and expressions. Okay, so what are we doing? So here I'm saying I want to sort anything that is a sortable range. And now I do a vector of string, I do an array of 128 integers and a list of integers. And basically, you can look up what a sortable string is in the standard library. It's something that takes a random access range where the elements can be compared with a less than. That's true for a vector of strings, so this works beautifully. It's true for an array of integers, works beautifully. Lists doesn't provide random access, so this fails. So that's an error. Notice what happens. We have made implicit the type of the containers, the types of the element, the number of elements, the comparison of strings. All of this is taken care of because we've already told the compiler about this at some point. All we now have to do is to explain to the compiler what a sortable range is. For the previous couple of decades, we couldn't do that, so we got awful error messages if we made any mistakes. This could be spectacularly ugly. But we have to look into the manual, into standard, into whatever it is. And that's not good. We wanted to express it in code. So here's the ideals. I want this to be extremely general and flexible. I want zero overhead, and I want well-specified interfaces. Well, for a long time, we didn't know how to get all three. I spent a long time trying to figure that out. I asked lots of experts, and for a long time, nobody could do all three of those, so we got the first two. That was enough to make it spectacularly useful and spectacularly popular, but now we can get all three. Okay, so now the old style, we said we had type random access iterator, we had a comparison, we take a pair of iterator and we can compare. And for that, we get the spectacular useful thing. Here we have an array, a vector of string, and we can sort the vector, we can sort the array, we can sort the half of the vector, we can sort the vector with a different sorting criteria, and we can sort the array with a sorting criteria that's specified with a lambda, so that we get it ascending order. And here we have sorting with absolute order. This is very good. The problem here is that this is not very directly expressed what I just said. It simply says it takes two types, and the compiler has to figure out whether the code in that implements sorts works for the arguments you gave it. So we'll do that. That style of generic programming is used for sort here has been successful for the last 20-some years. Very general, very flexible, traditional, bit verbose, but horribly bad at error handling, very efficient though. And so it violates some of the ideals for C++. The interface is not precisely specified, and there's not enough information to do a decent optimization or decent error handling. Okay, so we have to define what it means for a template to use its parameter correctly, and here I'm defining sortable range. So a type R is a sortable range if it is a random access range and if it has an iterator that is sortable. Now, like in real code, in more code, we are not building straight from the language. We're using a library. The library here is in the ranges library in the standard. So this will work once you've done your import std and using ranges. And so this has been defined. And we have just taken a couple of pages of standards text and turned it into a couple of lines of code. The code is much more precise and simple to use. Whatever. We didn't do quite it. That's interesting. Anyway, we didn't do it quite generally enough because we have to have the two types, namely the type, a sort of a range have to take two types that has random access for the ranges and the predicate words.
Sometimes the mute button, this is why it disappears.
The mute button?
Yeah.
Where?
I see it. It's over there. This is what they told me. So be careful with the button you press. Okay, anyway.
No. Okay. Anyway, we have generalized it to something that has the generality needed for a standard library. This is not a toy example. And now I can do things like this. I have the vector, I can sort it. Oh, and by the way, I'm saying I'm taking a range. I'm not taking a pair of iterators. I can do that too, but I don't want to. Usually, look, I'm not pressing anything. So we can sort the ranges in decreasing order, and we can not sort the list, but we'll get the error message here. It can simply say that a list doesn't have a random access range. Fine. We have made an improvement. We have to remember, the important thing here is we can say precisely what we want. It's not actually the error handling. The error handling is a side effect of being able to specify things correctly. But the thing you see first of all is the error handling. Okay, so we can also build concepts straight from the language. Here I'm building an equality comparable function, concept I mean. It says that if you have a T and a U to be in equality comparable, you have to do this. You have to be able to compare them with equals and not equals, both directions. Fine. Having done that, I can now say I assert that int and double is equality comparable. Static assert is a standard facility in the language. If this doesn't succeed, the program won't compile. Simple as that. And it succeeds, of course. I defaulted U to T, so if I only specify one type, then it succeeds also. Of course, you can compare integers to integers. And I better not be able to quality compare integers and strings. This is a language like C++. It's not a scripting language where everything can convert to everything. And so concepts, you can write types that works for all suitable types. I have here, what is it? It's a find if that finds something that has a predicate. It can specify. You have to get a little bit used to writing the notation here. If you think that is complicated, try reading the specification, which says the same thing but takes half a page. Code is nice, and now I can find if in numbers something that does the string to integer of is less than 42 and such, just using a lambda again. So one thing to point out is we've always had concepts. No generic code will work unless somebody has thought about what the requirements are of the generic code on its parameters. So if we go in, Dennis put stuff in the arithmetic and floating concepts into the original C. We have the STL concepts. The math is full of concepts. The graphs is full of concepts. We've always had it, we just didn't have a notation for it in the language. And so that's what we've got now since C++20, and experiments, of course, for many years before that. A concept is a compile-time predicate. We can simply ask a type, are you a sortable range? Are you a number? Things like that. It's quite simple. Concept benefits, it supports good design because I can write down more clearly what it is I'm thinking. It's more readable, it's more maintainable, and it gives better error messages, and it allows overloading. I'm going to show an example of that. And basically, I think this for generic programming is an improvement comparable to when C++ got classes and where we got function prototypes in C, which by the way was my handiwork. If you write C these days, you're using some syntax and some facilities I put in back in the old days. There's the simplified design. I decided, what if I wanted to sort lists? We don't, because they can be quite expensive to sort if they're big. But what if? Then I simply design my concept sortable forward range, which is a forward range that is sortable. And then I can define a sortable function that takes a sortable, copy error. Compiler would have caught that. Anyway, so let's pretend that there's not a bug and I put the forward in the right place. So I have a vector and I sort it, I have a list and I sort it. You can wonder how you will implement sort. There are a variety of ways of doing it, like putting all the elements into a list and then copy that into a vector, so sorting. There's a variety of ways. Anyway, here, once you say sort, if you say sort V, it'll say, that is it's a sortable range, so we'll do it. Here it'll say it's not a sortable range, but it's a sortable forward range. And so it'll pick that one. So basically it picks the strictest requirement, and that's all there is to the overloading here. It's much, much simpler than general overloading as in the language. Simplifies design. We have anyway, I'm defining a couple of types that are popular. There's a smart pointer. It should have an arrow operator if and only if the type is a class. The element type is a class. So I can say that directly there. Or we can do a more interesting thing. We can have a pair that can be constructed from a different kind of pair, provided each of the elements of the pair can be converted, and you can express that. And try and do that in C++ 11, and you'll find this is a real pain. This is much cleaner, much easier. So what we are seeing here is an example of compile time computation. We do a lot of that in C++, has done it forever. Things like inlining was in the early days, overloading based on const, makes decisions based on the type system. Here we can do just about any function, anything that can be evaluated by compile time. We just call it a const expr function. The compiler checks that it can be compiled can be evaluated if you give it constant values. If you insist that they are evaluated at compile time, you call it const eval. and concepts is an example of that, except that they have a slightly different syntax and can take type arguments and use them as types. And since they can't have side effects, they can't access non-local data, they can't have undefined behavior, and they can actually do a lot. So this is the C++, modern C++'s version of a pure function. It's a pretty good approximation of most definitions of pure functions. And so here's an example. Somebody in a Japanese embedded systems firm asked me if they could have a compile time integer square root. I'm not quite sure why they wanted an integer square root. I think they were computing distances, but I don't know. So basically I defined it here. It's the simplest algorithm I know for calculating a square root. And now I can say the integer square root of 1, 2, 3, 4 is 35. If I couldn't say that, I would have to calculate it on the side and build a magic constant into the program. That would be sort of all right for integer square roots. They don't change very often. But a lot of the places where we want constants have to do with sizes. How big is an integer? How much memory have we got? Things like that. And in those cases, if we do a calculation on the side, put the stuff into the code, 10 years later, things may have changed and you now have introduced a bug without touching the code. And you can do this for generalized things too. Here I'm calculating Yule. I want what is the weekday of Christmas in 2024? Well, the answer is Tuesday. But the point is that we can do things at compile time for fairly complicated abstract things. This stuff is in the Chrono library. You don't have to implement it yourself, but it's an interesting library to look at. The code is quite clean, and it can happen at compile time, so it is blindingly fast. Does it matter? A lot of these things do matter. I haven't actually seen a resource leaks after basic testing for years. And my favorite technique for optimizing these days is to throw away all the clever stuff and see if it matters. And quite often, clever stuff involves a lot of pointers and dereferences and calculations, which are things that slows down modern computers and also confuses optimizers. So my rule of thumb is if I can't understand it, neither can the optimizer. This doesn't follow all the time, but it's a good rule of thumb. And once I wrote a system, not a time system, something that's been in production use for 20 years in a critical application, and it accidentally got 100 times faster. I was deeply shocked. This doesn't happen. Mostly it was because I had removed stuff that I found complicated to understand. A lot of it had to do with concurrency, so I can't show it here, but basically if you write clean code, sometimes you get really pleasant surprises. And if you don't, you can measure it and then tune. So basically, I don't use more complicated than stuff than what I show here. Most of the time, of course, experiments are less constrained. You express lots of complicated stuff. I know the same stuff about milk and cows and management, such as Jose Daniel mentioned earlier. There's at least 2 major companies in the world dealing with cattle and pig farms that is using C++ for that. Concurrency, apologies, there's a lot of stuff there. We need it for efficiency. We have broad support in C++ for threads and locks, sharing, parallel algorithms. That's my favorite. If you can use a parallel algorithm, somebody else has done all the hard work. cooperative cancellations, futures, SIMD, there's lots of stuff. And so don't be stuck in the 20th century. That's old stuff. There's contemporary styles yield many benefits if you use them right. Upgrading code is hard. If you have 1 million lines of code written in the 70s, it can be really hard to upgrade it. That example there was 1990s code and written with what was fashionable then with optimizations that was necessary there, but it didn't it wasn't needed today. And new code doesn't have to follow outdated styles, so try not to carry the 20th century with you in your head. What you learned in school might not still be relevant. So how? How do we avoid being stuck with our old ideas? It is, as I said, very simple to mistake conventional for simple and new for complicated. So I'm working on guidelines and enforcement. We can't change the language. I mean, one of the great benefits of a standardized, long-lived language is that code written 10 years ago, 20 years ago still works. And that is the real guarantee that code you write today will work in 10, 20 years. And so if you are among the people that care about that kind of stability, this is important. So we can't change the language. We can't just throw away all the old stuff we don't like anymore. Partly because not everybody dislikes the same things, and partly because we simply can't get away with it. And it wouldn't make any sense. So we need guidelines for how to write the new code. And I've worked on that, something called the C++ Core Guidelines. This is a project that outlines useful ways of writing code done by a variety of people. And it's available now. However, people can't follow guidelines. It's too complicated to apply a whole set of guidelines on a large code base. It helps. It helps with code reviews. It helps guide people to write good code. So it's not useless, but it's not perfect. So we need to enforce guidelines, and that's known as a profiles project. Basically, a set of guidelines defines a way of doing things, and a profile can verify in the code that it's being done. And that's being worked on in C++, in WG21, which is the official name of the Standards Committee, and elsewhere. It's not yet available, unfortunately. It's a way of addressing technical debt. You'll be able to pick a profile saying, check where we are violating this kind of stuff. Where are we, say, subscripting raw pointers without range checking? Kindly find for me all the cases where that happens. We can do such things, but it's not standard yet. So this works on the philosophy of a subset of a superset. People say, well, give me a subset of C++ that's safe. People have been saying that for 40 years at least. And the point is we can't do it because the facilities people need to build advanced stuff uses the simpler, unsafe stuff. So I cannot build a vector without having pointer arithmetic. So what we want to do is we want to extend the language with a set of libraries. And then, once that's available, we can remove the old stuff that we don't want to use in general. So, say new and delete for memory management belongs down there. Vectors and lists and threads are up here. We don't need to go and fiddle with the low level anymore. So basically, extend the language with the library. We have the STL, we have a tiny library called the GSL, guideline support library. And what we get is basically C++. It's more elegant, it is faster, and it's not as big. So we don't want to neuter things by putting in endless checks or restrictions. And so the core guidelines is things like it's broken down because people can't apply all the rules at the same time. It has to have gradual introduction. And people will need additional rules for specific areas. If you are in, say, aerospace, you will have some real-time constraints on your code that will not exist if you are writing things for, say, text manipulation in a normal environment. So we initially focus on the core rules, and the things I really want is the core of the core. No uninitialized variables, no range or null pointer violations, no leaks, no dangling pointers, no type violations, and no invalidations. We have a fair amount of experience with this. Some of it is available. Some of it you can get in Visual Studio, Static Analyzer, in the Klangtidy, and what is the Sea Lion has some of it too. Not all of it, but it's getting there. I'm working to try and get it into the standard. So let's see an example here. Here is some old style that is a source of a lot of mistakes. People pass a pointer and sometimes a size to make sure that you don't get a range error, and so you call it and everything's fine, provided n really is the size of this one, and provided it really was available to check. Usually it's just a pointer, usually it's an integer, and it's just about impossible to check. In general, it's impossible to check. Not just difficult, impossible. The hoarding problem gets into this. And here we have a mistake. Since I'm using explicit numbers here, we can see it. Again, if this was I, it would not be easy to spot. And so we need to make simple things simpler. So we make an abstraction, which is basically a range. It's a span, it's a pointer, and it's the size of the thing pointed to. This is what we're talking about here. I was talking to Dennis Ritchie about it 40 years ago. He wanted fat pointers, as he called them, and the C Standards Committee wouldn't give it to him. Anyway, span is in the core guideline support library, and it's now in the standard, also standard library. And I can say I want a span made out of A. That's verbose. We already told the compiler that A was an array of integers of 100 integers, so it knows that, and we don't have to say it. And as a matter of fact, if we have to put a number in there, we have to use a slightly different syntax, more explicit, which means that this one will stand out. So if I do a code review, we know that there's something to check. If we're a static analyzer or compiler, we can see that there's something there that's suspect and decide how to deal with it. So it's simpler than the old style, it's shorter, it's at least as fast. Make simple things simple. Here's the one that I'm working on. We have test cases that works this. This is what's called invalidation. We have a simple looking thing here. We have a vector. We do a pushback. Here I have a vector. I grab a pointer to an element, point into it, That's suspect, but we do it a lot. I call F. This is fine, and then I use P. Now up here, we extended the vector. It now has 3 elements. That means that the elements may have moved, meaning that this one may or may not write into the elements that we did before. This can be caught statically. If you read some of the papers that we are proposing here, and if you look at some of the references to this, you can find experimental implementations. This is not, well, it's experiments, but it's not vaporware, because I'm not trying to sell it you for money. It's experiments that is being done successfully. So basically we need to catch this. So basically we know how to eliminate dangling pointers. Poof. And these are my list of profiles I would like to see. The reason for profiles is I don't believe there's a single standard library that provides the guarantees that everybody needs. So if we break down people's needs, people can apply it incrementally, people can apply it if and only if they need it in their world. And so what I really, really want is type here, initialization ranges, casting invalidation pointers. It basically makes code that passes the type profile fully type safe. Let's see, pointers, for instance, does 2 things. It prohibits subscripting of things where you don't know the size of the range, and it range checks. It has abstractions that range check things. And by the way, you can get hardened libraries today. They will become part of the standard in C++ 26. They're deployed today by Apple and Google. And it is not going to make it into the official standard. I think that's a major mistake, but implementations are underway, and some of them you can use. So you must request a profile to be used. So this is not something that sort of magically comes in and spoils your old code. If your old code is, if you're happy with that, leave it. If you want to more, I did not press it. Anyway, if you want guarantees, then you just ask for it, and you can get the checking done. So basically, C++'s model can be summarized like this. We have notice where my fingers are? Anyway, we have a static type system. We have the same rough support for built-in types and user-defined types. That was ideal from the beginning. This is why you don't have to say new to use a user-defined type. That's how you can have a pointer to a user-defined type. We have value and reference semantics. Value semantics is easiest to use, but you need reference semantics to implement it. Resource management, object-oriented programming, generic programming, compile-time programming, and directory use of machine and operating system resources. Concurrency support through libraries, that's important because concurrency keeps changing over the years, and by having libraries we can follow the fact of the way people use things and the hardware people uses. And then I really want to eliminate the C preprocessor, and I tend not to use it anymore for any code I write. None of the standard code I write. Okay, so this is how we're going to attack the idea of creating better libraries cheaper. And C++ was designed to evolve, and it did. There's the time scale of this. Every sort of few years, some problem gets solved. People get a larger and larger library. If people says, I want to know everything or use everything, they're probably wrong. What they should have is a set of guidelines that helps them use what's appropriate for what they're doing. And there's some reading material that backs up what I'm saying and gets into greater depths. There's the Hubble papers that Jose Daniel mentioned in the introduction. Yes, C++ is the only language presented 3 times, and I'm the only person to have presented 3 times. There was a reference to Daniel Eckert's paper on using modules. It also have loads of other uses of modern C++, and there's Khalil's paper on how to have really efficient exceptions, which actually is supported by a library. So if you're using Clang, you can actually download it and use it today. There's no science fiction in this talk, except the first slide of the Hitchhiker's Guide to the Galaxy video game, which was written in C++. Okay, I'll stop now and take questions.
Great talk, Bjarne. Thank you, and sorry about the giggling. So, questions?
Thank you. People have been trying to kill some technologies, in quotes, for a lot of years. For example, SQL. But SQL is there. With this quoting, people are trying to kill C++ from the safety vector. I assume that this profile mechanism in the standards committee is a way to improve in the area of safety. How strong is that pressure, the pressure to make it safer? Because we have other alternatives, and so, especially in the last couple of years, that people from the White House and so on have said that C++ is not safe enough and so on.
Okay, I have a long answer to this. First of all, people have been trying to kill C++ from before it was called C++. AT&T canceled the C++ project 3 times. Each time the manager who was trying to do that found that there wasn't a C++ project, it was just me. And I was in research, couldn't cancel me. And each time I managed to extract resources out of him and her, there was one, because they depended on it. Secondly, the US Department of Defense tried to kill it. They even passed a law against it back in the 90s because you really, really had to write Ada. Ada, by the way, is a much better language than its reputation, but fine. So what's happening today is people keep going on about C/C++. And you may have noticed that I'm not a fan of writing code the way it was done in the mid-70s. We can do much better. There are problems that people say you shouldn't use C++ because, and something I haven't been doing for 20 years. So I think it's a lot of the criticism of C++ as a language is unfair by emphasizing the worst aspects of the oldest way of using it. On the other hand, just because something is unfair and inaccurate doesn't mean that it doesn't work as a criticism. It seems that a lot of people who would like to try some other language, notice the list of languages that we've seen. JavaScript? You want to write safer code by using JavaScript? But if you like JavaScript, you now have a way of attacking C++. What do you want to do next? Write your JavaScript engine in JavaScript? All of the JavaScript implementations are C++. I mean, it's a C++ application, etc. So, yes, they have a correct point is that a lot of people aren't using C++ well enough, but that's not the way it's expressed. It is C says C++ is bad, don't use it. It is not. What I agree with is that a lot of people don't use C++ well. A lot of the techniques that make C++ good cannot be done in C. When I started with C, it couldn't do function argument checking. That was one of the first things, and I had 10 years of criticism for incompatibilities. But now you can't actually write C without using some of my early work for making it safer. So I think we should have profiles. I think we will get profiles. I think we will see implementations of the profile framework deployed by major compilers this year so that you can ask for a profile. You have a standard name for a profile. You can suppress the profile where you need to. That's equivalent to other languages, unsafe code or trusted code. And I think we will see a couple of profiles deployed this year, including the range checking profile, which by the numbers I have seen is 70% of the security violations. So I expect by Christmas I would be able to say we have eliminated 70% of the problems people go on about. And we haven't broken the billions of lines of code that is already working. You don't actually need security checking in all code. Some code are behind serious firewalls. Some things are not connected to the web, etc., etc. But yes, I think we need profiles. I'm in favor of profiles. I've been working on it for a very long time. The early checking of core guidelines profiles are now 7 or 8 years old. This is not new stuff. I think with a bit of luck, the criticisms over safety will strengthen C++ and improve it.
Thank you. More questions?
Professor Bjarne, may I ask what's your symbol on the top right of your slides?
Oh, well, we'll cut the cable. It's the crown with engineers' hammers sticking out of it. It is the logo of the Columbia Engineering Department.
Okay, thanks. Okay.
Columbia was founded under the English royalty before they invented the United States. So they used the crown, and since in the engineering department there has to be hammers.
More questions?
Hello. You voiced your disdain for garbage collectors. How do you feel about borrow checkers?
Could you just say that again? I'm not sure.
Excuse me? Hang on. Okay, I get it. You gotta keep it closer. Yeah, I'm sorry. You voiced your disdain for garbage collectors. How do you feel about borrow checkers?
I dislike garbage collectors. It's one thing. And I do it because they are unpredictable, because they require more resources. A copying garbage collector means you need twice as much memory, roughly, and because they are not general. And any comments about borrow checkers are separate. I don't see those two things as relevant. A lot of code becomes more complicated if you have to have a borrow checker. In particular, I don't think that in general no aliases is the correct solution for the best way of expressing an algorithm. And so it complicates coding. I actually tried to solve a similar problem with specialized pointers back in 2002 and such, and decided it fouled up too many of my algorithms. And in particular, if you look at how to express the C++ standard library, you find that things like merge and such, and all the algorithms that can work into the same data structure will go away. You can't do it. So there's people who says, well, you should just use C++ with a borrow checker. The problem is it won't be C++, because loads and loads of the key libraries, not just the standard libraries, but also in graphics and such, will no longer work. So I think that a borrow checker is too restrictive for people interested in algorithms. On the other hand, you can get things that are roughly equivalent, and I've done so in real work, by saying, well, this particular pointer, this particular container will not have aliases. So I saw a bug that was equivalent to the invalidation thing that I showed you. That is, there was two threads. One thread sent a container over to the other one. The one and kept using it. They had a lock on it, so that it wasn't a concurrency bug. But one of the sides did a pushback. And so the solution to this was very simple. We provided a vector that couldn't resize, and used that instead. And the problem went away. Meaning that if you have that kind of problem in the context of concurrency, use a more specific pointer type that doesn't take aliases, or use a container that cannot invalidate. That's a simple solution today. My invalidation checking, which is done with the C++ core guidelines, with Herb Sutter, people from Red Hat, and Gabby Does Raise, can actually detect if you have that problem statically, and you can fix it today. And there's zero overhead.
Thank you.
More questions?
Thank you. My question is sort of an aggregation of the last two, which is in the topic of killing technologies. People really like to use not strawman, but let's call them strawman arguments on why something's bad. And obviously memory safety and all those things come up around C++. regardless of having really memory safe constructs such as atomic reference counting, like what's it called, smart pointers, and all those kinds of things already in the language. So my way of looking at languages is that people have to be, as a community, striving towards an explanation of why their technology is good. And I think C++ really falls back behind. So my question is, how do we, as a C++ community, strive forward to work around the strawman artifacts and actually show the power of C++?
I can say I'm trying, and it's obviously very hard. From day one, I was noticing that we couldn't teach teachers fast enough. And people were teaching uses of C++ that I did not recommend and I actually recommended against. And that's still happening today. So what we can do is to show good coding rules. We can talk about good coding rules. We can write textbooks and courses that teaches C++ as if it's the 21st century, as opposed to people writing, say, a whole book about how to use pointers. A lot of the pointer problems come because you use pointers as ownerships or as references to containers. This is just wrong. I try currently, I have 2 books out there, one for people who are already programmers, the tour book, which basically only show raw pointers for explaining how to implement the better abstractions and how to make stupid mistakes, explaining to them that it's stupid mistakes. And then I have the Swan book, the principle and practice of programming using C++. And that one is just for beginners, has the same kind of strategy. The only examples that has the problems that I don't like in terms of language are the examples of how not to do things. And we need many more articles about this, and we need many more talks about this. A lot of people write their talks for the conferences that basically is, look at this very complicated advanced stuff. No, we also have to have a constant emphasis on how to do the basics right. And I was just looking at some of Jose Daniel's stuff. He's building a course that more or less fulfills these ideas. So yeah, you're in the right place here.
You spoiled my question because I wanted to ask you what is your view on how you should approach to teaching and what recommendations you give to students in the way they should approach to learning, but I think you mostly answered that.
I can say a little bit more. And one is that my reach is not as far as I would like it to be. I can write articles, but there are people who don't read articles. I can give talks, but people really want more concrete things. So we need tool support for it. This is why we need profiles and not just guidelines. And we need a whole variety of approaches. Some people look at videos, some people read books, some people read short articles, long articles, different kinds of courses. C++ is just far too big as a community for a single approach to apply. So look to see where you can do something good. Look to see where people aren't doing it. Show how to do things in concurrency. Show people how to do in generic code. Show people how to use things in embedded systems. People are doing this. It has been done, but it's not reaching the millions of programmers that are using C++, and it's most certainly not reaching the vast majority of teachers and trainers because they are focused more on existing code and existing practices.
Yeah, before 2014, we were using lots of libraries to use containers that today are in the standard library, and we thank you for that because it's excellent and stable and elegant. And now we have a sort of the same problem with AI, trying to adapt to hardware, where we use intrinsic. I have some code that uses intrinsics, and you can get a lot to do just simple things like dot products efficiently for the CPU, for the GPU, if there is. Do you have any plans of putting, because of course we have very good libraries for linear algebra, etc., but they're rarely optimized and they're rarely using the hardware the best way they could. Do you have any plans to put that into the standard library?
Let me say a word and then I can see you're itching to answer. And this is good because he knows more about this than I do. First of all, I'm not an expert in AI. And secondly, the variety of concurrency is rather large. So we are working on something in the standards committee, but it's going to be slow coming. And so you're not going to be perfectly happy very soon, but we are trying something. Having said that, I'll hand it over to Jose Daniel that works more directly in this.
There are a couple of things that, if everything goes well, we should have in C++ 26. One is an abstract way of expressing SIMD instructions. So no more intrinsics for SIMD instructions, no more Intel intrinsics or ARM intrinsics. You will be able to express this as with a lever interface. So that is something. Then the next thing in the short term that we will have is a linear algebra interface. So basically, BLAS level 1, 2, perhaps 3 will be in the standard library and will be implemented by your provider. That is something also that you might perhaps have in C++ 26, if things don't go so well, might be 29. And then after that, there are more things on the works for the long term with things like statistical estimation and some other things that might be quite useful for machine learning. But let's go step by step.
It's probably worth mentioning that anything we say, it might be in C++ X, will exist in C++ X-3 or such as experimental implementations.
Yes, SIMD, for example, is already experimental, and if you go to cppreference.com, which I assume many of you go from time to time, you will already find the description of the interface and a pointer to some reference implementation.
Yeah, so for the past decade, C++ was evolving a lot, no doubts, but in my opinion, C++ 11 was more than that. It was like a revolution. The question is about history. Why it took so long to get C++ 11?
First of all, it simply takes time to figure out what the problem is and what the solutions are. Secondly, you then have to do the experiments to show what works. And then you have to convince a large number of people that really this is a problem worth solving and it's the right solution. And you have to convince them that even though this is not perfect, because it never is, it is worth having. And that takes time. In C++ 11, there was a lot of things. Let's take an example. Const expert, constant evaluation. This was deemed by some important members as being not only useless, but also unimplementable. And we had some of the strongest opposition that I've ever seen in the committee to const expert. It spread like wildfire, and everybody is using it, and I see C adopting similar things to it. The committee is a strength in the sense that it provides a lot of expertise and a lot of enthusiasm. But it's also, under ISO rules, a consensus-based thing. And you need consensus. And with new people coming in, people with different backgrounds and such, it's very hard to convince people. Last time I checked, there was 527 members on the mailing list. Getting them to agree on anything is really, really hard. And usually people will agree to things that have only local impact. We can do this kind of thing here and it doesn't affect the rest. But the thing that really matters is when things work together. And that's hard to get through the committee, and it's getting harder. I think that contracts were ready many years before it came. I think that modules were ready somewhat before they came. I think we could have had pattern matching if people hadn't been busy arguing about obscure details and not getting the fundamentals right. I think we could have had contracts in a good form 6 years ago. Having a large committee with sort of one person, one vote is not a good model for how to evolve a language. It's not even a guarantee against silly decisions. And it's certainly a block on speed.
More questions?
Friend outside told that I have to ask a question, so here we go. This is also related to SIMD, and I have noticed that a lot of people are more aware that what SIMD is and what it can do, and we have like loops, and compiler can optimize these loops to use SIMD in them, and but we have object-oriented programming where we kind of have data structures that are kind of a little bit deviating and getting us out from this kind of easily optimizable loops. So is there something that how we could make people to understand maybe that how to construct their data so that the compilers would have easier time to optimize with SIMD? And can this kind of help be done by C++?
I think two things. One, SIMD is something that most users of C++ doesn't understand and won't understand. I believe that the best way of bringing this to the masses, to the other 95%, is to provide algorithms that uses SIMD under the hood. Because I don't believe you can get somebody with a 3 months introduction to programming to use it well at the SIMD level. Then we need a standard for SIMD interfaces so that SIMD code will be portable. And then you get the education problem. It is really, really hard to teach people a new concept at scale. If you sit down with a couple of bright people, you'll succeed. If you want to reach 1 million, you will fail unless you think really hard, choose a focus, back it up with tools or libraries. And so, to get what you want, you basically have to do it yourself or gang up with a similar minded people and provide information to the kind of community that could be approachable for that. It's not something that a standards committee can handle.
Anything else? I do have a final question. If I go back to the design and evolution of C++, and I go to the principles and ideals that you had, I have kind of two questions. Is there something in those lists that you really regret? And the second is there something there that you still didn't get?
Now, I haven't read it all recently, so I'm not sure I can give a really straight answer. But my impression is that most of it was pretty good, because I was being cautious and because I was trying to think about the long term. And there will undoubtedly be things I muttered about and didn't get. Like, I think modules are somewhere, if not in the list, then in the backup of the lists. And I only just got it a couple of years ago. So I think I was rather lucky with the philosophy parts of design and evolution of C++ and the lists of principles and such. And the reason I was lucky was probably that I had been working on this for about 10 years. And also because I felt the need to write this, because people were coming with suggestions. You must do this, you must do this, you must do this. Every feature that's ever been useful in any language had been suggested. And I soon realized, we go back in the early 80s, I realized that you could not design a language based on looking at this feature, that feature, that feature. You had to have some principles, you have to have some ideals, and then you have to articulate them. And D&E was my most serious attempt to do that. There's a bit more in some of my talks, and there's a bit more in the Hubble papers. But I can't think of anything where I'm kicking myself. I said that or I didn't say that. One thing I failed to do well enough was to explain the use of exceptions in error handling. And people have mistaken how to use them and what they were for. And people have been inventing things that create their own problems without actually solving the problems. Like, I don't understand why expect that has a cost whenever you use it, because you have to you have to pass more information. But I don't understand why it doesn't throw an exception if you fail to test it. Because now you have the information necessary to see if an error happened, but you can ignore it. And things like that. If I had written more about error handling, in general, I think we could have avoided a lot of problems. So if you go and look at the lists, maybe there should have been more about error handling.
Thank you very much. So thank you everybody for attending. Thank you, Bjarne.
Thank you.